So welcome to the Orphy Department Colloquium. It's really a great pleasure, unfortunately not in person, but okay, so it goes, to have Peter Bartlett come give us a talk. So in some sense, Peter, of course, needs no introduction, but I'll introduce him nonetheless. So Peter's a professor at Berkeley in EECS and statistics, and he works mainly on machine learning and statistical learning theory. And then, in addition to quite a number of administrative roles, Peter is the associate director for the Simons Institute for the Theory of Computing, which is a really wonderful institute for those of you that haven't had a chance to interact with it. I really learned a lot from some of the programs I attended there. And, on a more personal note, I'm kind of a newcomer to machine learning, and I've enjoyed reading a lot of Peter's papers, although certainly not even close to, a lot to all of them. I remember being really impressed and enjoying the VC dimension papers, which are a little bit older now. Then there were some margin-based complexity-bound papers for neural networks, which were really great. And he'll tell us about a recent really exciting article called Benign Overfitting. So please take it away, Peter.
All right, thanks very much, Boris. Thanks for inviting me. Sorry that I can't be there in Princeton. So this is joint work with Phil Long, who's at Google, Gabor Lugosi at Pompeu Fabra in Barcelona, and Alex Sigler, who's a PhD student in statistics at Berkeley. And it's on this phenomenon of benign overfitting that really emerged from the practice of deep learning. So practitioners have demonstrated that these deep networks can be trained to zero error on the training data, even for a regression loss, and still achieve near state-of-the-art prediction accuracy. Most surprisingly, even when there's noise in the problem, and when we know there's noise in the problem because it's been injected into the problem. So there's this very interesting paper by a group that at that time at Google who looked at the performance of deep networks on a particular prediction problem. On the x-axis in these graphs is the level of noise that's been injected into the labels in this problem, and they trained for a training set that was corrupted in that way. They trained various deep network architectures until they got essentially zero error on the training data. This is showing how long it took to do that training, and then the bottom graph here is showing on the y-axis the performance of those networks. And what's particularly interesting is the degradation in performance as noise is introduced. They're getting a near perfect fit to the training data, even when we know there's noise in the problem, and still there's a graceful degradation. The performance is pretty good for noisy training data. So that's been observed in other contexts. The astonishing thing is there's no trade-off here between the fit to the training data and the complexity. They're using as complex a function as is necessary to give a perfect fit. It's certainly fitting better than we should expect because it's giving an empirical risk that's much smaller than the noise level. So certainly overfitting in the literal sense, but this overfitting is benign in the sense that it doesn't affect the prediction accuracy of these networks. So that's a pretty astonishing thing. Classically, we're used to this sort of trade-off between the fit to the training data and the complexity of a prediction model. So maybe if we're minimizing the squared error over a sample of XY pairs, a sample of size n, we'd have some trade-off between that fit to the data and the complexity of the prediction rule, the f hat that we use here. And maybe that complexity might be controlled in terms of the number of parameters or the scale of those parameters, the norm of a vector of parameters, or more generally the norm of some sort of of our prediction rule, if it lies, for instance, in an RKHS, or maybe some other complexity parameter like the bandwidth of a smoothing kernel. When we're in a non-parametric setting where the number of parameters is growing as the sample size grows, this sort of trade-off has always been viewed as crucial. You find it in textbooks. We teach it to our classes. You shouldn't be fitting the data too well. A fit to the data that's better than you expect is one that's likely to not be a reasonable estimate. That's the classical statistical wisdom. And the striking thing is that these deep networks are fitting to noisy data too well. They're trained to fit noisy data perfectly, and still they're predicting well. So, you know, that's a really exciting phenomenon. There's been a lot of interest. It really, people started thinking hard about this at a spring 2017 program at the Simons Institute. And since then, been a bunch of work. You know, a bunch of people that were there, Misha Belkin and Daniel Su, and Sasha Rachlin, had a whole lot of work in this direction, looking at a variety of different prediction methods. More recently, a whole lot of work by, so for instance, there was this paper on exact asymptotics of linear prediction methods, Trevor Hastie, Andrea Montanari, Saron Rossett, and Ryan Tibshirani. You know, and lots of other works. I guess it's growing as we speak. It's a popular topic. What I want to tell you about today is focused on the linear setting, but actually for all of the, so linear prediction problems with squared loss, but actually for all of the results that I know about, you know, the real intuition behind this benign overfitting phenomenon in the cases where we've seen it occur is that the prediction rule can be split up into two pieces. One of them that's a simple piece and one of them that's a spiky piece. The simple piece is useful for prediction. The spiky piece turns out is not. It's useful for overfitting, for getting a perfect fit to the data, but it's benign. It doesn't hurt prediction. And you know, the simple piece is all of our classical you know, mathematical statistics sort of understanding applies there. And it's this spiky piece that's that seems to be the interesting and novel piece. So, you know, we'll see a couple of examples of this along the way, including the linear prediction case going to be focusing on for most of today's talk. So there's a review paper on a bunch of this stuff with Andrea Montanari and Sasha Rachlin that's going to appear in Acta Numerica, just to advertise that you know, kind of spells out this intuition. So one nice example is a classical approach of kernel smoothing. So this is an Araya-Watson smoother. You know, you have your XY pairs, and a kernel smoothing method takes as the prediction rule at a point X a weighted sum of the YIs, where the weighting depends on how far the test point X is from a training point Xi. So this K is a kernel that's a function of that difference, divided by the sum. So it's a non-negative function divided by the sum. So you get a weighted combination of the YIs. And Misha Belkin, Sasha Rachlin, and Sasha Sipakov studied this sort of kernel smoother in the unusual case where your kernel is singular. So as the test point approaches the training point, you know, you have this 1 over the norm to some power, which means that this value goes off to infinity. So there's a big spike at 0. That spike means, you know, your weighted sum approaches 1 at each of these xi's. So your f hat is interpolating. So, you know, they showed actually that even though you're doing this crazy thing that's perfectly fitting the data at every test point, at, you know, under suitable conditions, you can get minimax optimal rates for estimation in this sort of setting, for prediction in this sort of setting. You can view that in these terms, right, as a combination of a simple component and a spiky component, where the simple component is working with just a compact kernel, just doing the usual averaging, usual analysis of the averaging that another Araya-Watson kernel approach takes, and that's good for prediction. And then there's a spiky component on top of that that lets you interpolate the data, but doesn't actually have very much effect on prediction at all. You know, it's a spiky piece that gives you a perfect fit, but it has a small L2P norm, which means it's not helping or hurting the predicted accuracy. Okay, so that's one very nice example. The one I want to focus on in this talk is linear regression. And you know, we focus on this setting because it's one that we can easily analyze, right? I think it's really the aim is understanding this phenomenon of benign overfitting. I'm not advocating interpolating methods for linear regression. But that's a setting that we can get a fairly complete understanding. So we'll start by carefully defining the set of problems that prediction problems that we're concerned with, and we'll see we can get a quite precise characterization of when benign overfitting will occur and when it won't. And then we'll look at some of the implications. So there's this phenomenon of adversarial examples that appears with deep networks, that you can make small perturbations of for instance, an input image and have a huge change in the prediction of the function as a result of that small perturbation. We'll see, this is an inevitable consequence of benign overfitting as a sort of if and only if in the linear case. We'll look at some generalizations to ridge regression. So where you're going right across this spectrum from interpolating through very small levels of regularization up to classical levels of regularization, and we'll see we can generalize this characterization of that case. And finally, I want to say a little bit about the sorts of analyses that that can or cannot be applicable in understanding this phenomenon of benign overfitting. And we'll see a couple of examples there of approaches that are just not going to be informative about this phenomenon. Okay, so that's the agenda. Let me start by talking about by giving a few definitions. What are these linear regression problems that we want to deal with? So we have XY pairs. The covariates X we're thinking of as lying in a Hilbert space. You can think of them as points in RD, but the infinite dimensional case is really no different. We'll use matrix vector notation throughout. So so it's really the notation is suggesting we're working in RD, but things can be infinite dimensional. And we have a real valued response, and we'd like to use the X's to predict that real valued response. The truth is actually linear, so we're in the well-specified setting. The conditional expectation of Y given X is the inner product between X and some vector theta star, or some element of the Hilbert space theta star. And we're assuming our XY pair is mean zero and sub-Gaussian, so nicely behaved tails. And the X has to satisfy a small ball condition. These are the assumptions on the probability distribution that we see. Some notation here, 3 pieces of notation. I guess we've already seen the theta star. We have a covariance matrix, which is the crucial quantity here. In some sense, directions don't matter. When we take the spectral decomposition of the covariance matrix of our covariates X, the eigenvalues are important here, and this we're writing them in decreasing order. So this is some notation that's going to be important throughout most of the talk. Theta star we've met already. It's the parameter vector for the optimal linear prediction rule, and sigma squared is the noise level. All right, so this is the notation that we'll need, and we'll maintain that throughout. And we're considering a particular interpolating prediction rule. It's the minimum norm estimator. So this is the rule that we have a sequence of XY pairs. We'll write that as a data matrix X, where the rows are vectors in our are the covariate vectors. There are n of them, and Y is our vector of responses. And our estimator, instead of X transpose X inverse X transpose Y, we're in the high dimensional setting where the dimension of our parameter space is higher than the sample size. We're considering the pseudo inverse of this X transpose X, all right, which is the solution to the optimization problem. When you're minimizing the performance on the training data, the squared error for a parameter vector theta, subject to solving that minimization problem, you want to find the minimum norm solution. Okay, and the kind of figure of merit that we work with here is the excess risk, the excess prediction error. It's the expected squared error of our estimate theta hat versus the optimal. This, of course, is our sigma squared. And you know, we can write that as this expected squared error for the prediction based on theta star, and of course, you know, this covariate vector x is mean zero and has covariance sigma, so we can just write this as a quadratic form involving this difference between our estimate theta hat and theta star. And of course, you know, this is telling us about the role that those eigenvalues play, right? The directions that correspond to the big eigenvalues are the ones that really matter. You know, we better get our estimates right in those directions. The ones that correspond to the small eigenvalues, you know, we can afford to have a very significant error in our parameter estimates. Okay, so that's the figure of merit we're going to work with, this excess prediction error. We want to know how close we can get to the best linear prediction.
Quick question.
Yeah.
So
sure.
just to make sure, you're also assuming theta star is unique. Like there's nothing that's orthogonal to the support of the x's or something like that.
Yeah, yeah, so let me think. So you know, if you have some direction where there's a lambda that's zero, then you're in some subspace of the original space, right? I mean, that doesn't really change anything in our whole setup.
I see. So you just restrict to that, and then you take that theta. Okay, right. Thanks.
Right. Okay, so let's think about this minimum norm linear prediction, minimum norm interpolating prediction rule. And if we think about that as a sort of limiting case of a regularized of a ridge regression problem, right? So this is our fit to the data. It's the sample average of the squared error for our this is our data matrix, you know, squared error for a parameter theta. This is a, you know, classical ridge regression formulation. You can, of course, write this optimization problem in the equivalent form, get the best performance on the data subject to some constraint on the scale of the parameters. And you know, that constraint, of course, depends on the regularization coefficient lambda. It depends in a data dependent way, but you know, there's a correspondence between these two. But there's another way of writing this optimization problem, and that is to minimize this term subject to a constraint on this term, which is, you know, the form that we're really thinking of here. Minimize the norm of this parameter vector subject to a constraint on the performance on the data. And the surprising thing that we're working with here is this constraint on the performance on the training sample is kind of too good to be true, right? We're interested in this overfitting regime where that constraint is much smaller than the best we can expect, right? The minimum of the expected loss, right? So we're wanting the sample average to be much better than the best we should hope for. And you know, of course, in our case, in the interpolating case, we're working with c equals 0, which is sort of the limit as lambda goes to 0. But later on, we'll see we can work with the full range of these parameters. Okay, so that's the kind of estimation, the kind of theta estimate that we're working with. And we're thinking in this overfitting situation where the dimension of the space is big enough that you know, actually we can always get zero empirical risk on our sample. So our estimator is the minimum norm interpolating solution, right? So for every XY pair, we're coming up with a theta hat that gives a perfect fit to the data. And really asking the question, you know, we want this excess risk to be small in this case. So we're asking the question, you know, when we choose this minimum norm interpolating solution, we're taking the label noise that's in these Ys, and in some sense, we're injecting it into our parameter estimates, right? Because we're matching all of these Ys, and we're asking, you know, when can we do that, hide that label noise in our parameter estimates without hurting the predictive accuracy? Okay, so here's the
Okay, let's give Peter a second to reconnect.
Suspense.
Exactly. I wonder if it's planned. It's the most exciting. So here's the theorem, but
That
that was very suspenseful, Peter.
wow. So I lost my screen. Everything went blank. Let's try that again. How's that? Can you see it?
Yeah.
All right. And you heard what I said up to this point? I don't know when I
Yeah. It just
okay.
cut out before the theorem.
Yeah.
Great. I didn't know how long I was flatlining there. Okay, so so there's a certain notion of effective rank here. We're taking the highest variance k directions and ignoring them. And when you look in the orthogonal subspace, the effective rank of the covariance, a certain notion of effective rank of the covariance in that orthogonal subspace is this little rk of sigma. Once that's big enough, so once you've eliminated enough directions that that effective rank is big compared to the sample size, so it's just some universal constant b, let's call that k star. And the result is that, there we go, that the excess risk is bounded by, I'll say something about the bias term in a moment. The really interesting term here is what happens to the noise. Question here is what happens to the noise. So this is the interesting term, the variance term. This is the noise level. We get two pieces to the variance term. One is k star over n. So this is the dimension of that subspace before we have this tail condition, right? So that should be a low dimensional subspace compared to n. And the other grows with n, but it's n over another notion of effective rank of that subspace. Okay, so we'll see what these are in a moment, but you can see that that subspace better be high dimensional, certainly much larger than n if we want the excess risk to be small. Okay, and we can't hope to improve this upper bound by more than constant factors, because you can get a lower bound that's effectively exactly the same thing, modulo constants, under some additional conditions. So the data now is the covariate vectors are a linear transformation of a vector that has independent components. And the theta star, to get the bias term exactly right, there exists a sign pattern that has exactly the same theta I star squared terms in it to get exactly the same bias term. So this is telling us there's no hope of improving this upper bound by any more than a constant factor. One thing we'll come back to later, but I mean, I put it in small print here, the bias term. Crucial thing is that one component of the bias term is for everything but those first k star dimensions, you're paying a cost in terms of the bias that's exactly the same as if you predicted 0 in all of those directions. So we're really doing no useful prediction outside this k star dimensional subspace. Okay, so that's a point that we'll come back to a little later. Okay, so let me say what these effective rank conditions really mean, what these notions of effective rank are. The first one, little rk, is once we've eliminated or ignored the first k, the highest variance directions, we consider the one norm of the remaining vector of eigenvalues of our covariance matrix divided by the infinity norm. All right, so this is a notion of effective rank. It's kind of how many of these biggest eigenvalues fill up the trace of what's left. And capital RK is rather similar, but instead of a ratio of a one norm to an infinity norm, it's a ratio of a one norm, squared to a two norm squared. Okay, so so these are those two effective rank quantities. Just to get a little intuition, there we go. Okay, then they're not too far from each other. The capital RK is bigger, but not too much bigger. This is a sort of elementary property to prove, just using the ordering of the eigenvalues. then to think about a few examples, you know, obviously if these are all the same, then this is just measuring dimension, right? So if we start out with an identity matrix or scaled identity, you know, it's just the rank of the matrix. And you know, for a finite rank matrix, you can write it as the rank times some notion of asymmetry. So, you know, this little s and capital S are looking at kind of, again, it's like an L1 norm to an L infinity norm and an L1 norm to an L2 norm. And these both lie between the smallest value they can have is 1 over P when you're very asymmetric. You know, there's really only one lambda 1 and everything else is close to 0. And they could be as big as 1 when all of the lambda i's are equal. So, you know, this is sort of the symmetric case gives you, when you have this symmetry of the levels, you get the highest effective rank. Okay, so so that's what these little rk and capital RK, they're the definitions, and you know, you can see now, right, what you want is that the effective rank of that tail of eigenvalues is big compared to the sample size. Once you cross that threshold, and it should happen quickly, then you'd like this other notion of effective rank to be really big compared to the sample size. Okay. In terms of this intuition, the story I described earlier, you know, really fits in exactly that way. The prediction rule, you can split into this simple component, which is the linear prediction rule in the K star highest variance subspace, you know, corresponding to these biggest values of lambda I. And then this other component, which is the overfitting piece, right? That lets us fit to the data, but it doesn't have much of an impact on our prediction accuracy. So, you know, it doesn't have much of an impact precisely when this effective rank capital RK star is big compared to the sample size. Okay, and actually that bias component that I mentioned earlier is showing that this orthogonal piece plays no role in prediction accuracy. It's as if you're predicting 0 in that orthogonal subspace. You don't do any better than that. Okay, so you know, where does the result come from? The mix of eigenvalues of the covariance matrix plays two roles here. It tells us how we're going to be taking that label noise and distributing it through our parameter estimate, because, you know, we have to fit to every noisy label. And then, of course, it affects the excess risk, and we saw it's determines that quadratic form. It's you know, it tells us how errors in different directions of our parameter estimates affect prediction accuracy. And it's the combination of these two that give the characterization. So we want that noise energy, turns out, to be distributed across lots of directions that have these low values of lambda I, that are low variance directions, unimportant directions. And of course we need many of those, a large effective dimension, effective rank of that tail of the covariance matrix compared to the sample size. Okay, and I said all of this, and you know, these notions of effective rank are telling us that actually we get some extra benefit from having those small eigenvalues where the noise is going to be spread, being all roughly equal. This is a more helpful situation for us. So let me say just a little bit about the ideas behind the proof. You know, I'll give you a kind of a cartoon picture of it. We think about the excess expected loss as breaking up into two components: one that corresponds to the best linear prediction rule, and one that corresponds to the noise, the contribution of the noise. And we get, you know, two corresponding sources to our excess loss. the parameter estimate is a distorted version of the true parameter because we have a distorted view of the covariance of our covariate vector X. And you know, being in a high dimensional setting doesn't really change the story here. The other part is much more interesting, and that's the contribution of the noise, and that's what's really different about this overfitting scenario, is that we're corrupting our estimated parameter vector with the noise in the labels, and that's a much more interesting component, asking when we can hide this label noise in our parameter estimates without hurting the accuracy. Okay, so if we split things up in this way, we split up the labels into x times theta star plus a noise component epsilon. This is our minimum norm interpolating estimate. It takes this pseudo inverse of x transpose x and multiplies it by x transpose y. I'm going to write it in that way, and our excess risk is this quadratic form. And of course, when we split up our parameter estimate into these two pieces, the signal and the noise piece, we get two components to our excess risk. First one, you know, we can deal with in a rather classical way, and I'm not going to go into it. The one that's the impact of the noise is much more interesting. You know, looks like this. And when we you know, write out our excess risk in terms of the contributions in the different directions, ordered by the variance, the level of the variance in that direction, we can split these into the high variance directions. Let's say the first K of those, and then the other ones, the light directions. You know, it turns out when we have this effective rank condition satisfied, then our eigenvalues are all concentrated around the sort of trace of the rest. I should say the eigenvalues beyond this point, right? So once we go past those first K directions and look in the subspace orthogonal, all of those eigenvalues are about the same. So this condition ensures that kind of the biggest eigenvalue isn't giving us any problems, and it's the bulk that everything is concentrated around. So we have you know, n non-zero eigenvalues of this x transpose x, which is a very high dimensional thing, and you know, there are the first K, and then beyond that, from K plus 1 to n, they're all about the same. And in particular, if we looked at, you know, the Gram matrix, the matrix of inner products, which is an n by n thing, then that matrix is nicely conditioned. You know, we have all of the eigenvalues bigger than this quantity row, which is reminiscent of a ridge regression setting, right? So our theta hat with the pseudo inverse of x transpose x, we're guaranteed that the smallest non-zero eigenvalue here, with the pseudo inverse, we're ignoring the zero eigenvalues. The smallest non-zero is bigger than rho. So it's a lot like adding a rho times I component, which we do in ridge regression. Okay, so there's a kind of effective regularization that's arising here. And then you could just track where the energy from the noise goes. We look in the different directions, the eigenvector directions, you know, in a direction VI that has a corresponding eigenvalue lambda I, we get a noise energy from that direction in our parameter estimates. That noise energy is proportional to n times lambda I, right? Because you know, n of these little lambda I contributions. It's scaled by something like rho to the minus 2, to the minus 2, because we're thinking about energy here. And then that impact on the prediction error is scaled by another factor of lambda I. Okay, so you know, the impact of the noise energy in that direction on the prediction error is something like n times lambda I squared over rho squared. And okay, that's for the lightest directions. In the heaviest directions, we can do better than this. You know, you can bound them in terms of just a 1 over n, and sum those things up over all the directions. We get k over n plus n times, you know, 1 over this capital RK. Right, so the lambda I squareds from this piece, and the 1 over the sum of the lambda i's all squared from the rho piece. So that's the whole story. That's really the intuition of where the noise goes in terms of excess prediction error. Lower bound is a very similar story. I'm not going to spend much time on that. And just to go back to the theorem statement. So that's what's going on in the linear regression setting. You can ask now, well, when does this quantity get small? You might hope to have, as the sample size grows, you might hope to have this quantity going to 0. But that's kind of complicated thing, right? Our effective rank here depends on the sample size. We have this k star divided by n. We'd like that to get small as n grows. Both of these, of course, are functions of n. Similarly, for this term, we'd like that to get small. So in terms of understanding when we might have nice asymptotics for one of these, a sequence of linear regression problems as the sample size grows, this bias term is somewhat problematic because it depends on a kind of interaction between the optimal parameter and the covariance matrix. If we upper bound this in terms of something that depends only on the norm of theta star and ask, when does that excess risk, or that upper bound on excess risk, right, that no longer depends on anything about theta star beyond its Euclidean norm, when does that upper bound go to 0? We get an expression like this. We want to know for what sequences of covariance matrices do we have, this quantity going to 0? Okay, you can play games with sequences of eigenvectors and try and understand this quantity. And it turns out, if you're in an infinite dimensional setting, it's a bit of a peculiar situation, right? You look at polynomial decay of the eigenvalues, and the only case where you have this limit being 0 is when you're right at the edge of a summable sequence of eigenvalues. This alpha has to be 1, and you have some sufficiently large power of the log term. Okay, so it's just almost diverging, and that's the case where this thing goes to 0 as the sample size grows. So that looks like a very unusual situation that you might not expect to see in real problems. It turns out things are quite different if you truncate to a finite but large dimension. If you're in a finite dimension and you have a fast decaying piece, for instance, let's think about an exponential decay to our eigenvalues, plus an isotropic piece. So in all directions, there's this small variance, epsilon n. So as long as the dimension that we're in, Pn, is large compared to the sample size n, and as long as the total noise energy from the isotropic piece, so epsilon n times Pn, is small compared to the sample size n, but not too small. It can't be tiny. You can't be in a effectively finite dimensional setting. So as long as it's small isotropic noise energy, then you're in this benign situation. As n grows, performance will you'll get closer and closer to the optimal, and you can make that quite quantitative, right? It's like the isotropic noise energy divided by n. Okay, so that's a more generic phenomenon. You've got this quickly converging sequence of eigenvalues plus an isotropic component. Then as long as you truncate at some finite but large compared to sample size dimension, then you have this benign overfitting phenomenon. Another situation where you have it is, rather than a fast decay plus isotropic noise, if you have a slower decay that's truncated at some level, then you'll get the same thing. So if the dimension is big compared to the sample size, you have a slow decay, then you're in the benign situation again. So that seems like a much more universal phenomenon when you're truncating at a finite but large dimension.
So question, Peter. So how should we reconcile that infinite dimensional thing with the finite dimensional ones? Should we think that like in infinite dimensions, what we should imagine is that maybe first the eigenvalues decay rather rapidly for a while, and then the asymptotics kick in, and then eventually they just decay polynomially. But
Yeah,
somehow we
so
already don't care about those or something, or what's
right. So they're actually, I mean, writing down eigenvalues that decay like a polynomial is sort of the first notebook attempt you'd make, right, to think about how these things would change. But I'm not sure it's a particularly informative example. Another case where you do have this benign situation is where your eigenvalues are changing in steps, and the size of the set of eigenvalues that are roughly the same at each step is growing. And this is actually exactly the situation that you see with something like an NTK, right? So if you think about you're in a reproducing kernel Hilbert space, the kernel is defined by a polynomial in an inner product in Euclidean space. Then you can think about the eigenfunctions of that thing. You go and work them out, and you get, it's all of the polynomials of a certain degree. So there's a growing number of those as you go up in degree, right? And the eigenvalues are stepping down as you go up in degree. And that's a situation where you also have this this nice property. As the sample size grows, things get better and better. So I think thinking of these polynomial decreases is maybe not the most informative example.
Yeah, I understand what you're saying. Thanks.
All right. So okay, so let's think about some consequences of this of using this sort of minimum norm interpolating solution, and what are some consequences when when it's performing well. So there's this phenomenon with deep networks of adversarial perturbations to examples, that you can find a way to perturb an input by a very small addition of a very small change that can lead to a very large change in the prediction that a deep network gives. And we've seen many examples of this. This is a really striking phenomenon about deep networks. In the linear regression setting, it's kind of an obvious thing that if you're taking all of that label noise, you have a linear map that goes from the y vector to the theta hat. If you're introducing noise in that, so energy that's growing linearly in n, then you're going to see something growing with n in your theta hat. And you should expect that to be bad news, right? There's got to be some direction in parameter space where that noise gets transformed. So you take this x transpose x pseudo inverse x transpose y, and that linear transformation of the noise vector gives you a direction where you've got a lot of action, right? You can perturb your inputs in that direction, and you're going to have a huge change in the output. And this is just an easy calculation, but that thing, you can see that the change that you'll see in that direction is big as a function of these eigenvalues. And turns out you get a lower bound that if the excess risk is below some level epsilon, then the sensitivity to a unit norm change here is huge. It's like 1 over square root of epsilon, at least 1 over square root of epsilon. So this is just based on one of the terms that's in the excess risk here. So having benign overfitting in this situation leads inevitably to huge sensitivity to changes in the input. There's kind of, it's an if and only if. Another way of viewing that through this sort of intuition about the two components to our prediction rule in one of these benign overfitting situations is that this this delta component, the overfitting component, is there to, plays the role of fitting the training data perfectly. So it has to have a big L infinity norm to match all of the noise, but it's benign, so you need its L2P norm to be small. So this is kind of inevitably a spiky thing, and you should expect this sort of sensitivity certainly around the training examples where you're matching this noise. In the linear case, it's telling you there's this whole direction that works everywhere in the input space.
So another question about this, Peter. Do you know what the smallest exponent P is, so that the LP norm of your delta is still small?
I
Somehow.
do not. That's an interesting question.
Just because that would give some sense of how, like, what sort of perturbations you're allowed or something like that, right? Relative to something about the dimension, number of data points, and the spectrum of your thing.
Right. Yeah, no, I don't know. This is an interesting question. Okay, let me say a little bit about ridge regression. So this is joint work with Alex Sigler. Alex is really driving force behind this work. So here, we're extending things from just the interpolating case where we're getting a perfect fit to the training data to through small levels of regularization with a L2 regularizer, all the way up to the classical regime here. So we have a ridge regression optimization problem, and I've written it as pick the minimum of the norm, the vector with minimum norms subject to minimizing this criterion. Of course, if lambda is greater than 0, then this is a unique minimum. If it's not greater than 0, then we're back at our minimum norm interpolating problem. So we have this whole sort of range of problems for all these positive values of lambda. Yeah, as I say, it covers that spectrum of situations, and you can really get essentially the same result. I mean, this is kind of dismissing a lot of the analysis, but effectively everything that we saw before has this sum of the tail of the eigenvalues replaced by lambda plus that sum, right? Where lambda is this regularization coefficient. One striking thing, and I guess I shouldn't be saying the optimal lambda when you're writing it as an optimization problem like this. It's when you write the solution of this optimization problem in the form of x transpose x plus lambda I to the -1 times x transpose y. It turns out that if you have this effective rank being really large compared to n, your optimal lambda might actually be negative. Because it may be that introducing decreasing that empirical covariance estimate in all directions is the right thing to do, because that can decrease the bias without significantly increasing the variance, which is an essentially high dimensional phenomenon. You won't see that when in the classical p less than n sort of regime, of course. Okay, and as I say, the theorem there about the excess risk is exactly as before, but where you're modifying things with this lambda, even down to the bias term, exactly as before. Okay, let me finish. How long do we have? A few minutes. So let me finish with some recent results about what sort of analysis tools might be useful in a benign overfitting situation. So, just stepping back, when we're thinking about understanding prediction accuracy of methods, we have an algorithm that returns some prediction rule. It might have empirical risk small. We'd like to know, what the expected risk looks like. Typically, we're exploiting properties of this prediction rule like it's something simple. In the case of deep networks, maybe the spectral norms of the matrices at each layer, parameter matrices, are not too big. Maybe the parameters are simple in some other way. There's some sparsity condition or rank condition or whatever. And we'd like to understand when that's enough to ensure that the true risk, the expected loss of our prediction rule is also small. So we might like to get a model dependent bound, so something that's a function of our prediction rule, probably a function of the sample size as well. And you know, function of a prediction rule here might, for instance, say, well, if this thing involves, you know, a small product of spectral norms, or maybe it's a linear function that has a small norm, right? We'd like that to be enough to tell us that actually the true risk is also small. Typical approach is using uniform deviation bounds, like maximum over some class of functions that have small spectral norms or some other nice properties of parameters. Supremum over that class of deviations between expectations and sample averages is not too big, right, as a function of properties of the class and of the sample size. So, you know, clearly when this quantity is small, then this quantity is, you know, close to it, no more than kind of twice this plus that. So that's great, but there are cases. So you know, it'd be nice to understand if this very classical style of analysis is applicable in the benign overfitting setting. So there's this recent work of Nagarajan and Kolta that comes up with a very nice example to show that, you know, this sort of uniform deviation bound is unlikely to be, is certainly not going to be immediately applicable in many of these situations. So they have a case of a classification problem, so certain probability distribution where you know, taking a single gradient step with effectively doing a naive Bayes kind of classification gives you something that has empirical risk 0, nice accurate prediction, but because of the symmetry of the distribution generating the data, you can see that any uniform deviation bound for any class of functions that contains the function that's produced must be too loose to be useful. So, you know, quite a striking example. Okay, that's in a classification setting without noise. In a linear regression setting with noise, you know, where we can make a statement about any model dependent bound. So let me give you a few definitions before we see the result. So we're considering linear regression with these least norm interpolants. That's theta hat is that estimator. We've got a bound epsilon that depends on our estimate, depends on the sample size, depends on some confidence level. We say it's a uniform model dependent bound if the excess risk is bounded by this quantity for all sample sizes and all deltas, right? So with high probability, our excess risk for this prediction rule is bounded by this quantity epsilon, and that's whenever we have some nice probability distribution, sub-Gaussian one. We also need that it doesn't increase too rapidly with the sample size. We might expect this bound to decrease with sample size, but we want that, you know, it doesn't increase too quickly. So, you know, if we double the sample size, we don't have more than a constant factor increase in our bound. Okay, so you know, under that condition, oh, and one more definition we need. There's a the intuition of this definition is, you know, being able to say something about most natural numbers. So, you know, we satisfy a certain condition in a strongly beta dense way beyond some sample size, means that, you know, when you look at sets of sample sizes above n naught, sample sizes n above n naught, sets of size kind of square root of n, most of them, proportion at least beta of them, satisfy this condition. So that's what this strongly beta dense means. Okay, so So, you know, with those definitions, the result is that you can come up with these nice distributions, and actually these XY distributions are, so the D here needs to grow with the sequence. I've drawn it as written as a constant, but it's not. Nice sequence of distributions of growing dimension where you know, the X's are Gaussians and the Y are sub-Gaussian, so that if you've got any one of these bounded antimonotonic uniform model dependent bounds, epsilon, the least norm interpolant has a very nice behavior, right? The excess risk is like 1 over square root of n with high probability. And yet, for most sample sizes, so there's this strongly dense subset of sample sizes for which this bound, which, you know, the excess risk is actually like 1 over square root of n, the bound is terrible, right? It's got to be as big as a constant. So, you know, you can't hope to have a bound for an minimum norm interpolant that just pays attention to the properties of that prediction, of that parameter, of that prediction rule. So they're fairly natural joint distributions, right? Gaussian and sub-Gaussian, and tells us that we can't have this sort of bound that doesn't increase too quickly with the sample size. And it certainly can't be tight, right? Needs to be quite likely bigger than a constant, even though the excess risk is going down like 1 over square root of n. Okay, proof idea is just based on the notion that, you know, if you're interpolating the data, then you're performing badly at the training sample points, and it's hard to distinguish that situation from a situation where the data is drawn from a nice benign overfitting distribution. I'll skip over that, and you know, just to summarize, I'll stop there. You know, we've seen in linear regression the importance of overparameterization. We need this high dimensional subspace where the noise can be buried. It leads to sensitivity to adversarial perturbations, and we can extend things to ridge regression, and we've seen these limitations. The you know, really exciting direction, I think, is we have a fairly complete understanding in the linear case. You know, what happens in nonlinear cases, particularly deep networks. You know, do we have the same sort of decomposition into a simple piece and a piece that's useful for benign overfitting? All right, I'll stop there. These are the papers that I've told you about if you're interested in those. So thanks very much.
Okay, let's thank Peter for a wonderful talk and open it up to questions, maybe. So maybe let me start with the question while people are gathering their thoughts. So about this very last thing, you know, it's quite interesting that, you know, you sort of prove that if you have this benign overfitting, you're gonna, at least in some sense, maybe in an L infinity sense, have to have adversarial perturbations. But is there any hope to then do something to make the resulting model actually robust? You know, you went through and you had this overparameterized model. Is there some way of compressing it or projecting it to make it actually not so overparameterized to help yourself, or is it just baked in and there's nothing you can do?
Right. I mean, what we saw there was that if you consider this minimum norm interpolating solution, then there's an if and only if, right? It's either going to be robust to small perturbations and have a terrible excess risk, or it's going to be really sensitive and have a nice small excess risk. I mean, it's right. So, but that is just one estimator. That's a minimum norm in interpolating one. So, you know, that certainly doesn't rule out doing things with some other with some other estimator that performs well and has a different properties in terms of sensitivity to input perturbations.
Yeah, exactly. I can imagine, you know, trying to obtain your estimator by some version of just gradient descent, but then somehow along the way trying to inject some kind of noise like people do in practice using some sort of data augmentation or whatever to try to, you know, more or less extract the signal you're getting from the min norm thing, but try to learn to be slightly more robust. I'm not sure if that kind of thing is even conceivably possible using your setup.
Right. I mean, you know, just viewing it as the norm of a function, you know, this minimum norm estimator is the one with the smallest smallest parameter vector, right? So anything else has a direction in input space where its sensitivity is even worse. So the linear case is sort of too easy to be very interesting, I think.
Yeah,
for that sort of question. Yeah. But yeah, I mean, I think this is a really fascinating question for nonlinear functions like deep networks.
So Peter, so let me just ask a natural question. So in your duration, you heavily use the square loss, right? So that your population sigma is there. So is this benign overfitting phenomenon continue to hold for, let's say, logistic regression, or are there kind of like wide margin loss or something like that?
Yeah, that's a really good question. So I don't know of analogous results in that sort of case. I know of Song Mai and Andrea Montanari, possibly a third author, had an exact asymptotic calculation for logistic regression sort of setting, where they show, you know, similar things actually beyond the linear case, looking at the nonlinear case as well. You know, where there's a similar sort of situation. Yeah, so you know, you can imagine for other losses where you can give a finite prediction and get zero loss, and they're just a different shape from a quadratic loss. You know, you could imagine considering a minimum norm estimate there. It's exactly the same estimator, and you're just trying to understand the different impact on expected loss, excess expected loss in that case, right? The estimator doesn't change. But yeah, that's a really good question. I haven't seen that analogous sort of analysis in those cases.
Thank you.
But as I say, these exact asymptotics, you know, has been worked out for the case where there's the truth is a logistic model, and you go ahead and work with a minimum norm estimator, for instance.
More questions for Peter?
Hey, Peter, I'll ask a question. So there's been some recent papers in the deep learning, deep neural nets, where they look like empirically, they've seen that what the deep networks do, they memorize some of the examples, and then they generalize a whole bunch of other examples, and that's how they get to this very low training error. Which seems similar to the, at least the inspiration of what you talked about. However, at least my understanding from those papers was that this memorization part it does impact the test set performance. So if you just eliminate all the examples, for example, that are memorized, you actually get your test set performance to be lower. And so it's different from your setting, where the delta, the spiky one, it has no impact on the test performance. So I was wondering if there is any interesting sort of parallel connection there.
Right. So so there's a distinction between splitting the prediction rule into these two components and splitting the training data into, you know, two subsets. And you know, you could imagine in the linear case, for instance, that there are examples that still have some component that's good for prediction in a particular xi. So in our case, that would be, you know, the component in that K star high variance subspace that's useful for prediction for that example. And then there's the piece in this orthogonal subspace that's really only good for matching the noise that that particular xi saw in its corresponding yi. If you throw away these examples that, you know, have a noise that means they get a noise component that means they get a big error, then you're losing information about the parameters in that other subspace, right? And so you could imagine that a similar sort of thing is going on, that there's, you know, two components to the function, and there's useful information in some sense everywhere.
Yeah. Okay. Cool. Thanks.
I mean, you know, this is all speculation in the nonlinear.
Of course.
Okay, maybe if there are no more questions, we can thank Peter again for a very nice talk. And yeah, try to enjoy the rest of the day.